This lesson discusses the probability of compound events. We'll call this part one. There's a part two also on my website if you're looking for more example of compound events. Okay, question number one. A box has four cards numbered 1, 2, 3, and 4. Charmaine will toss a coin once and record the toss as a head or tail. Then she will randomly pick a card from the box and record the number chosen. So first of all, she's tossing a coin. She's going to heads or tail. And then she's going to pull a card out of the box and get the number 1, 2, 3, or 4. So those are the possible outcomes: a head and then a 1, a head and a 2, a head and a 3, a head and a 4, and so on. So there's 4 times 2 or 8 possible outcomes, 4 cards and 2 sides of the coin. So 4 times 2, 8, because you got 2 events going on. All right, so there's the whole outcome space that I had right here, all the possible outcomes. And then give all the outcomes that it is tails. Well, you could have a tail and a 1, 2, 3, or 4. Number 2, suppose that the genders of 3 children of a family are soon to be revealed. An outcome is represented by a string of the sort GBB, meaning the oldest child is a girl, the second oldest is a boy, and the youngest is a girl. The 8 outcomes are listed in the table below. Note that each outcome has the same probability. For each of the 3 events in the table, check the outcome or outcomes that are contained in the event. Then in the last column, enter the probability of the event. So we have 3 things going on: the sex of the first child, the second child, and the third child, which, either girl or boy, or girl or boy. Multiply it together for the 3 different choices and you get 8. So there are 8 different outcomes that could happen. The first one, a boy is on the last birth, so a boy on the last birth, or the third birth. So that's 3, that one too. So it's 4 on 8, or 1/2. A boy on the first and the last birth. So the first and the last one is a boy. So there was 2 of those out of 8, or a fourth. 2 or more girls. So 2 girls, 3 girls, because that's 2 or more, so it could be 3 of them. Or this one, or that one, so there's 4 out of 8, or a half. Number 3, there is a bag of 3 balls numbered 1 to 3. There is also a pack of 3 cards lettered K, Q, and J. As a trial of an experiment, a ball was chosen and a card drawn. The number 1 to 3 of the ball and the letter K, Q, or J of the card was recorded. So you got 3 choices for the balls, and you got 3 choices for the card. So 3 times 3 is 9 different possibilities. So they want to know what's the possibility of a 2 or a 3 and the letter Q. 2 or 3 are the letter Q. So that's 2 of them out of 9, or 2/9. And they wanted it as a decimal, so divide, and that's 0.222. The next one, they want the experimental probability. Okay, so that's different than the theoretical probability. The theoretical probability is just what is the probability of it. And there were 2 of them out of 9. The experimental probability is using the chart up here. So they did 550 trials, and the experimental probability of getting a 2 and a Q or a 3 and a Q were 58 and 62 out of a total of 550 trials. So when you divide to the nearest thousands, it's 0.218. And with a large number of trials, the difference is going to be small between the experimental and the theoretical probability. The more trials that you do, the closer and closer you get to the theoretical probability. So experimental, use the table and the trials that you did by hand. Theoretical, you just think how many is it out of total. So there were 2 of them out of a total of 9, so 2/9. Number 4, an ordinary fair die is a cube with numbers 1 through 6 on the sides. Imagine that such a die, I have to do it. Here we go. Here's some dice for you. Imagine that such a die is rolled twice in succession and the face values of the 2 rolls are added together. This is recorded as the outcome of a single trial of a random experiment. So you could have a 1 and a 1. So a 1 and a 1, which has a sum of 2. Or you could have all the way up to them both being a 6 when you roll it. So 2 6s, which add up to 12. So I made myself a chart here of 1 through 6 and 1 through 6, and I added them all up here in the middle. All right, so what is the probability of event A? The sum is greater than 6. Well, if it's greater than 6, that means it's 7, 8, or 9, and I highlighted those, and there were 21 of those out of 36 numbers. 6 times 6, 36 numbers in here. So that's 7/12. The probability of B, that it's an odd number, well, half of the numbers are even. You can add them up, and half of them are odd. So if you add up all the odd numbers there were 18 of them out of 36, or a half. Number 5, there are 9 acts in a talent show: a comedian, a dancer, a guitarist, a juggler, a magician, a pianist, a singer, a violinist, and a whistler. A talent show host randomly schedules the 9 acts. Compute the probability of each of the following events. The first 4 acts are the comedian, singer, violinist, and dancer in any order. Well, in any order means that it's a combination. The next one has somebody that has to be first: the dancer, the pianist, the juggler, and then the whistler has to be last. That means the order matters. That makes it a permutation. So they want to know, what is the probability of that happening? Well, this is going to happen one way out of the combination of 9 acts, and we're choosing 4 of them. So 9 combination 4 is 126. And the second one, there's one possibility out of the permutations of 9 permutation 4, which is 30/24. Okay, just to remind you how to use the calculator here to get those numbers turned on, then go to math. And, well, I need to enter the number first. I'm going to do 9 combination 4, so enter the number 9. Go to math, which is on the 3rd row down, the first key. Go over to the menu probability. We want combination, that's 3. Hit enter. And we want 4. 9 combination 4, it's 126. So then the next one, 9 permutation 4, so 9 math. Go down to choice 2, permutation, and 4, and that's 3024. All right, then, number 6. For an experiment, determine whether events A and B are independent or dependent. A hat contains slips of paper with the names of boys and girls in the class. A name is randomly selected and returned to the hat. The slips of paper are mixed, and then another random selection is made. They put it back in, it was returned. So event A, the first selection is a boy. Event B, the second selection is a girl. Well, being a girl has not changed because they returned it. If it's returned or not used and it's still there, then it's going to be, the second event is independent of the first event because it doesn't change the overall probability of what had been there. Because they put the name back in the bag like it never happened, everybody's still there. So when we do another draw of the names, everybody's still there. So doing that second event doesn't depend in any way on what just happened. So it's independent. Again, the key is the fact it was returned. So look for that in the words. So on the next one, you can see right away I circled the words, it's set aside. So a bag contains green and orange marbles. A marble is randomly selected from the bag and set aside, meaning they took it out. Then another random selection is made from the remaining marbles. So they put it on, so the next marble that we get depends somewhat on what we took out. So that's why it's dependent. So that it was set aside or taken out. The next one, they returned it. So since they returned it, it's going to be independent. On the next one, you kind of have to read this one. It says a family has 2 children. Event A, the older child is a girl. Event B, both the children are girls. Well, that depends on what we had the first time. The first one could have been a girl or a boy. So this one is dependent. Depends on what happened the first time in event A. Next one, a number cube with sides labeled 1 to 6 is rolled twice. Event A, the first roll is a 6. Event B, the second roll is a 4. Well, it doesn't matter at all what happened on the second roll. Just because we rolled a 6, it doesn't mean that the next roll is dependent upon what happened before. So that's independent. Number 7. A box contains 5 pencils and 5 pens. A second box contains 5 colored pencils and 3 crayons. One item from each box is chosen at random. What is the probability that a pen from the first box and a crayon from the second box are selected? Write your answer as a fraction in simplest terms. So we have two different events going on here. We got the first box that we're pulling out a pen from, and there's 5 pens out of a total of 10 in the box. The second event is that we're going to pull and see what happened the second time. And then a crayon from the second box. So if we get a crayon from the second box, there's 3 crayons out of a total of 8 writing utensils. So when you got more than one event happening or more than one probability going on, what you do is you take each event, write down the probability of it, and then multiply them together, and that is the total probability for both events occurring. So just multiply them up. So that made 5 times 3, 15 over 10 times 8, 80, which is 3/16. Or again, you can cancel diagonally or up and down. So canceling up and down, 5 goes in the 10 twice, and 5 goes in the 5 once. So that's 3/16. Or you can always use your calculator. Let's do it again on the calculator. So we got 5/10, so parentheses, 5 divided by 10, and then times 3/8, math, and then hit math, enter, enter. Well, you hit enter, and then math, enter, enter, and you get that 3/16 then. Okay, we got another multi-problem here. There's 2 things happening. Other people who fished at Clearwater Park today, 63 had a fishing license and 7 did not. Other people who fished at Mountain View Park today, 48 had a license and 32 did not. Suppose one fisher from each park is chosen at random. What is the probability that the fisher chosen from Clearwater had a license? All right, so Clearwater, that they had a license. 63 did out of a total of 70 people there. 63 plus 7, 70. Okay, and then that the fisher, they really should write fisherman, that the fisherman chosen from Mountain View did not have a license. You got to read. It says do not, did not. All right, did not was 32 of them out of a total of 48 plus 32, which is 80. So again, multiply the 2 probabilities together and you get 0.36. Again, on the calculator, you got parentheses 63 divided by 70, and then times 32 divided by 80, 0.36. And if you wanted to, you could hit math, enter, enter, and it changes it to a fraction. But they wanted it as a decimal because they said do not round. So if it says simplest terms, that means a fraction. If they want you to round your answer, or it says do not round, that means it's going to be a decimal. All right, number 9. A bag contains 10 marbles. 2 are green, 3 are red, and 5 are blue. Bob chooses a marble at random, and without putting it back, he didn't put it back. He took it out and he kept it. He chooses another one at random. What is the probability that both marbles he chooses are red? Write your answer as a fraction in simplest form. All right, so the first time he has 3 red marbles out of a total of 10 marbles. Well, he picked one of the red marbles, so that means there's not 3 marbles left that are red in the bag. Now there's 2 marbles left in the bag. And again, we didn't put the marble back, so we don't have 10 marbles anymore. We have 9 marbles. So 3 times 2, 6, over 10 times 9, 90, which reduces to 1/15. Again, you can cancel diagonally or up and down. So canceling diagonally here, 3 goes into 9 3 times, and 3 into 3 once. So we got 1 times 2, 2. Oh, I should cancel that way too. 2 and 10. 2 goes into 2 once, and 2 goes into 10 5 times. So you got 1 times 1, 1, over 5 times 3, 15. Okay, last one. A university class has 27 students. 13 are nursing majors, 8 are history majors, and 6 are psychology majors. The professor is planning to select 2 of the students for a demonstration. The first student selected at random, and the second student will be selected at random from the remaining students. What is the probability that the first student selected is a history major? Well, there are 8 history majors out of 27 students. All right, now we don't have 27 students anymore. We're going to have 26. And the second student is psychology. Well, we have all the psychology students still, so we have all 6 of them still. So there's 6 of those out of 26. All right, so the first one again, they wanted a history major. There's 8 of them out of a total number of students of 27. Then we had to take a student out because we didn't put them back. So now we have 26 students, but we have all our psychology majors still. All right, so just multiplying them together and then rounding it to the nearest 3 places or the thousandths, it's 0.068. All right, send me an email if you need to talk about this further. Thank you.